Okay, so welcome back to another video. So here today we want to show that the following equality is true, and we have that the base -1 to the power 1 plus 2 and then plus all the way up to n is equal to -1 to the power the ceiling of n divided by 2. So in a sense, we have like a little number theory proof we want to show. If you take a look closely, we have to deal with, because with the base is -1 and for both sides, it would have to depend on what our exponent would be. So -1 in the sense that the exponent would have to be like some sort of odd integer, positive odd integer, and then it will be equal to 1 when the exponent is an even integer. So if we're using ideas of this, we can actually apply using the modular congruence arithmetic to actually help prove this little, equality. And there's nothing more I really want to say because that's basically the entire premise of what this proof is going to be using. It's the idea of determining about the exponents of even and odd. Then after, exposing that whole idea with that, we use modular arithmetic / congruence to actually further show that you either get two values, but depending on what the even odds of those exponents are, the equality is still true either way. So let's actually just jump right in. So if you actually take a look closely on the left side, the expression of our exponent, 1 plus 2 plus all the way up to plus n, we notice that's actually the sum of the n natural numbers, and it gives us a nice close form that equals n times n plus 1 divided by 2. So we can actually just make this substitution and say that the base -1 of our given, and we just replace this with the close form of the sum of the natural numbers. So we have -1 to the power n times n plus 1 and then divided by 2. If you pay attention closely, because we have a divide by 2, then we would see that in order to get something in form of the integers of those exponents, then that has to imply that n times n plus 1 is always going to be even, because either way, either n or n plus 1 is going to be even. So I'll just say n or n plus 1 is even. Yet depending on whatever n choice your choice of n is going to be, of course it's got to be greater than 1 with this whole expression written over here. Then if we say this, then that would also have to imply that our given, well rather our new substitution for n times n plus 1 divided by 2, that would have to actually mean it's going to be always be in, an integer. Well, the exponent is always going to be an integer, and so this expression over here is going to equal -1 or +1, depending on whether the exponent is either even or odd. So exponent is either even or odd. So that's actually depends on this situation over here. So now we actually want to break this up even further and take a look at the exponent that we're dealing with. So if we were to take a look at the exponent and say that if n times n plus 1 divided by 2 is even, then there's a little bit of an observation we can make. So let me actually write this in another marker just to break up this case by case. We notice that if you take a look at things closely, let's say for example, we're gonna actually just do this by a little bit of, you could say trial and error, but more it's just playing around with numbers. So suppose that -1 to the power of some even, integer that's even. We'll start with 2, for example. So if I actually just solve, we get rid of the denominator from over here, so multiply to 2, so we have a n times n plus 1 is going to be 4. Okay, now say for example, if we have an even number for the exponent is 4, so do the same thing. So we have n times n plus 1 is going to equal 8. Let's try one more number. Let's say it's 6. So 2 times 6, so 12 is equal to n times n plus 1. If you pay attention closely, notice that those three numbers that we get, set that equal to n times n plus 1, they're actually divisible by 4. So by using modular congruence, we can actually say that we can actually define this modular arithmetic and say that this congruence is anytime with divisible by 4, that n times n plus 1 is going to be congruent. So in this case, if it's even, then we're going to get a remainder of 0 every time we divide by 4. So 0 mod 4, okay? Then if we see that this is going to be even, that is if, I guess I have to put this over here. So it's even, this has to imply that this is even if n is congruent to 0 mod 4, or it's either n plus 1 is congruent to 0 mod 4 as well. But we can also do a little bit of the arithmetic that says that for linear congruence, if we have some two integers, a and b, a congruent to b mod n is equal to a minus b divided by n. So we can actually just subtract the 1. And we're dealing with modular 4, so the cycle repeats at every 4. So 0, 1, 2, 3, then repeats. So if we're dealing with this, then that means we're going to get a remainder of 3 after we subtract the 1 to both sides. So that would have to mean n is congruent to 3 mod 4. That gives us the explanation if n is an even number, or n times n plus 1 divided by 2 is an even number. So now let's actually move on to when we're dealing with odd numbers. If we're dealing with the same situation over here, if I just play around the same numbers, you'll notice that this is what we're going to get for the following. So I'll say this again. So n times n plus 1 divided by 2 is odd. And that has to imply that this means that n times n plus 1 is actually going to be, well, rather, I'll say it like this. So if we're doing all that, then we're going to get that for each trial that we get, we're going to get that n is actually congruent to 2 mod 4. I wrote n, whoopsies, mod 4, or n plus 1 is congruent to 2 mod 4. But again, applying the same thing again, we can also say that n is congruent to 1 mod 4. If you just again play around with the same numbers, again, instead for odd integer, instead this is dealing with odd integers, we're actually going to get keep always getting a remainder of 2 every time we always divide this by 4 if we're actually performing that same modulo n is equal to 4 in this situation. And if we say the 2, then this is equal to this is equal to that. We can actually write this a little further and say that n is congruent to 1 mod 4 if this is going to be odd. So now we have these situations, listed. Then now we can also come to the conclusion and say the following, that negative 1 to the power n times n plus 1 divided by 2 is equal to the following two numbers. We have that it's going to equal negative 1 if n is congruent to both 1 or 2 mod 4, and it's going to equal positive 1 if n is congruent to 0 or 3 mod 4. So we have that established. Now, if we want to also make a little bit of an observation and say that the following. So now we see the observation we want to make is we say that observe negative 1 to the power n times n plus 1 divided by 2 is actually going to equal negative 1 to the power the ceiling of n divided by 2. Now that's kind of a little weird to say that stipulation, like to make that assumption over there, but we can actually do this with the following calculations given with these two results. So that's actually what we're going to do. So for this situation, for the first case we're going to do, so we're going to say for the first part, so for n is congruent to 1 mod 4, then suppose that we can actually let the equation n equals 4 times some multiple k, and then add this with the remainder of 1 over here, okay? And so that will have to mean that if we just plug this back to the equation over here, the right side, so we have negative 1, then the floor of n divided by 2, then that's just simply, you just plug this in, so negative 1 to the power the floor. So plug this back in. So this is 4k plus 1 divided by 2. So in other words, this is just 2k plus 1/2, and that's the ceiling. And so that's just going to equal negative 1 to the power 2k plus 1. But we know that 2k plus 1 is, obviously we can see when the terms with recurrence relations are this sort of sequence, then we actually get that this is, obviously we see that's the definition for odd numbers. And so negative 1 to the power of some odd number is going to always equal negative 1. So that takes care of that. So let's actually move on to 3 more cases. So now suppose for n is congruent to 2 mod 4. Again, just apply the same thing. So we let n equals 4 times k and then add this with the remainder of 2. Plug this back in. So negative 1 to the floor n divided by 2 is simply just negative 1 to the power the floor of, so this will be 2k, and then, what is it? Then we add this with 1. Then we take the ceiling back, then obviously then this is just going to give us the same thing. So 2k plus 1, and of course that's going to yield out a negative 1, because that's so an odd number over here. Okay, so now let's actually move on to the last two. So for n is congruent to 3 mod 4, then we say we let n equals 4k plus 3, then, well, obviously, so plug this back in, -1 to the ceiling of n divided by 2, then that's equal to -1 to the power the ceiling of 2k, and then add this with 3 over 2, then we see that this is just -1 to the power 2k plus 2. As we see here, this is actually going to give us an even number, so -1 to the power of some even number is going to equal 1. And so the last case is going to be a simple one. So we let for n is equal to 0 mod 4, basically we have a remainder 0, so in other words n is just going to equal 4k. Then we see that continuing further, then we have that we just plug this in, so -1 to the power the ceiling of n divided by 2. Basically that just equals -1 to the ceiling of 2k, which is just basically -1 to the power 2k, which of course that's just going to equal -1. So of course with these results, I'm going to underline just the key points. So we start off with this, we create a function, so, or rather we create an equation, and so after plugging the left-hand side, we get plugging the left-hand side, we get the right-hand side. So give me a second to actually underline the following. So now after doing all these 4 cases, that we can see that the following of the right-hand side is indeed going to equal the left-hand side. Using those similar results that we showed, that we either get 2 answers depending on our modular congruence of, the modular of f4. So therefore, we can actually go back to and finally conclude and say that -1 to the power 1 plus 2 plus all the way up to n is indeed just equal to -1 to the power the ceiling of n divided by 2. And just like that, we have proved our equality, and therefore it is complete. The video, I mean. So this is actually a really interesting, equality, especially in this world of number theory that we're actually using the following over here. So yeah, that's pretty cool if you ask me.